Hi, welcome to SPE Live. My name is Nils Korgesson-Low. I'm joining you all from a gorgeous summer morning here in Houston, Texas. It's going to be a real beautiful day. Temperatures just under 100 Fahrenheit, so cool by Houston summer standards. If you're joining us from earlier SPE Lives, welcome back. First time on SPE Live, then welcome also. Enjoy the show. SPE Live, like many of SPE's digital content, is made in part possible by sponsorship from the SPE Foundation. So thank you, SPE Foundation. Today, we are talking about completion fluids technology, and in particular, innovations in completion fluid displacement operations. So again, if it's your first time joining us here on SPE Live, you can interact through the chat boxes on social media. So tell us where you are from. We can already see, hi guys, good morning. You're already sort of saying hello from Ghana and stuff. So thank you. Thank you for joining us. Hello from Myanmar. Hello from Nigeria, Oman. Thanks guys, welcome. Welcome to our show. So like I said, we're talking completion fluids and displacement operations today. So ask us questions. We have a real expert in the studio. So any questions you have about completion fluids, including and especially displacement operations, then please ask us. So my guest today, I'm very pleased to be joined by Joey Detiveaux. Mr. Joey Detiveaux has over 44 years of experience in the oil and gas industry. 39 of these have been focused on completion and drilling fluids. So he has 9 years on me. 17 years with Millpark Intech Drilling Fluids, which is now part of Baker Hughes, and the last 25 years with Tetra Technologies. During his time at Tetra, he's had various managerial, operational, and technical positions, both here in the US and in Brazil. So that includes sales and subject matter expert for pay zone drill-in fluids, such as reservoir drilling fluids, area and regional sales manager, business development, technical and operations manager in Brazil, Gulf of Mexico applied engineering manager, US technical manager for completion fluids, and now currently general manager for US offshore completion fluid services for Tetra Technologies. Joey holds a Bachelor of Science degree in Petroleum Services Technology from Nichols State University. And he's told me before the program, the single most important thing he has learned while working in fluids operations is mud solids good, brine solids bad. So Joey is going to illuminate us all on what he means by this as we start talking over the next 30 to 35 minutes. So Joey, welcome.
Good morning.
Hi, good morning. So great to have you on the show. Great to see you. I love that little sort of saying there. Hopefully you'll illuminate us all about what you mean as we go through talking today.
So my early fluids life as a mud engineer, you wanted to keep the solids suspended. Now we want to knock them out, right? So.
Yeah, exactly. Yeah. So yeah, exactly that. It was suspension to flocculation and knocking them out. Yeah. So Joey, we're talking completion fluids and especially displacement operations today. I'm going to kick us off with a really dumb question. What is a displacement operation and why do we do it?
Yeah, it's no more than removing one fluid and put another in place. But, the challenge is keep them separated, minimize interface, design it to where it won't channel, depending on the well design, the geometry. But it sounds simple enough, but it's not.
So we're going to just replace one fluid with another. What's the reason for doing that? Why would we want to replace like the reservoir drilling fluid with something else?
Well, it goes back to, solids and having solids in one fluid and not in the other, right? So we're removing a drilling fluid, which generally is solids laden, and we're going to have to get it out of the well. We're going to remove all the particles, mud cake, mud film, the barite particles, get it all out, get everything. And more often than not, it's going to be a non-aqueous based fluid that you're removing. You'll want to water wet all the tubulars, right?
Yeah.
So that's what we'll end up doing. Remove the mud, clean the well bore, water wet everything. Now we are now ready to begin completion operations.
All right. Okay. That gives us a good perspective, so we can, sort of begin to talk more details from there. You have a lot of experience from Gulf of Mexico. And Gulf of Mexico has been one of these areas that's really innovated in many of the offshore technologies. Can you, actually, if you throw up the timeline for us, Joey, give us a perspective on how things have changed. How's technology been innovated over time with Gulf of Mexico in particular?
Yeah, and when I talk to this timeline, it kind of goes back, 30 something years, right? So back in '81, Tetra was formed, and we were a specialized high density brine company. And what we focused on was to remove the mud from the thing and put in place the high density brine, zinc systems, calcium bromide systems. And we designed the TDSP spacer system, which was designed to pump as slow as possible, right? And we're talking about surface stacks, right? Later on, we do that and we clean up the fluid with pod filtration. We introduce defiltration offshore. And we continued along our business. Everything's doing the same. We felt we were quite successful because folks were copying what we were doing. But then when you look at the line, as time goes by, the wells get deeper and deeper, and eventually you start with subsea completions, right? Subsea trees.
Yep.
And so we're talking about marine risers. Now, scoot along to 2010, Macondo happens. With Macondo blowout, following it, regulation changed. We were not able to use some of the methods that we were using prior to that because we're using a spacer system designed to pump as slow as possible. But when we're pumping risers, we're pumping as quick as we can. So there was a lot of interface and things. What we did was indirect displacements, and that is we went to seawater or some sacrificial fluid between stages, right? So here's the mud, we kick it out to seawater, and then we put it into completion fluid. That indirect displacement allowed us to get away with our sins, right, if you will. Now, following Macondo and with regulation, we could not go under balance. You had to maintain kill weight fluid at all time.
Yeah.
Then the challenge really got bad. And it's just not us. It was the industry. We all were playing by the same rules, and we're having bad displacements, right? We're not cleaning the wellbore. We're getting huge interfaces. And so I can remember a case we had to replace the entire completion fluid system, right? You're talking about like 8,000 barrels of fluid had to be changed on a deep water well, right?
Yeah, big volume.
Yes, large volumes, a lot of money.
Yeah.
So eventually, a few years back, we stopped what we were doing and realizing that we had to do something different. And if we were going to do it different, how do we do that? And how do we become successful again? So we took a lot of the deep water requirements, the large volumes of spacers, the high concentration of chemicals necessary to clean up. We designed the spacers to pump faster, right? So they hold together.
Yeah.
And we got out there and we started performing, and we've been performing at a high level. Later on, toward the end, I got a couple of case histories we can talk about, case studies.
Yeah, great. That'd be really good.
But we just had, since what we were doing was different, we had to do something different. It's just logical that you have to do something different. You can't do the same thing over and over in a different environment and expect the success that we once had, with different stacks.
So on that timeline, I noticed that there was some abbreviations. You had the TD SP, and then you had TADS. Can you just tell us what that means in terms of how the design of the displacement systems changed over time?
Yeah, well, we're very creative at Tetra. So TDSP is Tetra Design Spacer Fill. TADS is Tetra Advanced Design Spacer.
So what do they mean? Sort of how do they differ from like the earlier displacement operations that we did sort of 30 years ago?
Well, the first spacer, TADS 1, is a push pill. We looked at modifying the rheology. In the TDSP 1, we try to get as thick as possible to where we can pump it in plug flow, right? We try to hold that flat profile if we begin it. Now, in the TADS one, we have a rheology on it that allows us to pump quicker and it hold together. It's not going to channel. It's got enough suspension to maintain any solids that we have. When if we do use solids, we can actually do the whole spacer train TADS solids free if so desired, right? So we modified the rheology. We actually introduced cleanup in the first spacer versus just a simple barrier pill. It's an effective pill to where it's actually working to clean the wellbore. The second spacer, the wash spacer, if you will, is now strictly water wet, right? And then we still have a trailing spacer to pick up any solids, which, depending on well design, it's an option, if you will. It serves really no purpose. If you have a difficult design well geometry, say high angle S shape, you may consider leaving it out because it'll space out on you also, right? So those are the modifications that we've done. And with regard to the additives, we designed and formulated our own spacer additives to work at a high efficiency, very low dosage. And that aids us with some of these weighted spacers, not having to come back behind after cutting back the density with additives, weighted back up to what you need with salt. So we can effectively reduce the amount of salt necessary to weight back up.
Okay, so just say a little bit more for the benefit of our audience. And audience, please ask questions of Joey. If you've got questions about completion fluids or displacement operations, then just fire away here. Just let us know. We're watching you all on the chat here, so please ask questions. Joey, you talked about viscosity and in these displacement train pills. So there's 1 to 3 different pills in the displacement train. So there's chemistry, which has a function, but what's the function of the viscosity? Why is that important?
The function of this viscosity is to remove particles, suspend particles. The second spacer we want to get in turbulent flow, so we have no viscosity to it other than that of water or the brine itself. Again, on the first one, we have to maintain some particles. We have to maintain separation from the drilling fluid itself. And a lot of times it's a base oil peel or a water peel ahead of it, kind of, which we don't really need it any longer. We've done displacement without it. So you're keeping all these things separated. And again, what we want to do is be able to push the mud out the hole and not channel in the risers, right?
Yeah. Okay, yeah, so it's really about sort of preventing the fluid that's already in the well from mixing with the fluid that you're trying to displace with, right? So at the same time, you're trying to clean the well. So it's, as you said earlier, it's water wet. So do we just use the fluids or do we also use tools in combination? Or is it like two separate operations?
No, it's vital to have mechanical cleanup in there. We just simply deal with the chemical cleanup. Mechanical cleanup is very important too. You have to wipe. We can do, we'll never really get in turbulent flow in the riser. So you can mechanically wipe stuff out. Just about every displacement we do, we follow with a short trip, wipe the well board and circulate out again. There's a lot of verification with the tools that are run. Tools are very important to clean up also.
Okay, all right, thanks. So just picking up a question here from the audience already. So Carlos Jonathan Hernandez Mercado, he's asking, how do we clean a well with a long section, 13,000 feet, angle 45, and do a proper fluid displacement? I mean, Joey, is that a sort of typical well profile, or is that going to be a particular challenging one?
I think it gets challenging. Between 45 and 65 is clean, and you have different flow regimes. This particular thing, I'll try to get everything in turbulent flow, make certain that it comes up right. If if the rheology is not right on something like this, you just run the high side of the hole, right?
Yeah.
So, you'd want to rotate, reciprocate, design it to where you can get a turbulent flow, and you should be able to clean that well bore up pretty good.
Okay, thanks. So to go back to one of your earlier points, so after Macondo, things changed in terms of what fluid densities we were allowed to use in the well, and good for good reason as well. It's a big safety issue. So now you mentioned that we have to use higher density fluids. Can you say a little bit more about that? What implications that's had for fluid design in terms of, because you mentioned also having to reduce the volume of fluids at the same time. So what are those? Can you say more about those innovations?
Yeah, prior to that time or that event, we were able to kick the mud out, circulate seawater on the hole. We can, pump sweeps around and filter. We go about cleaning the rig, get everything, take completion fluid on, and then we just kicked it out. We went about the completion, right? Now it's a coordination between boats. You have to monitor barrel in, barrel out. So if I put one barrel in, I got to count for one barrel coming out. It gets trickier with pit management. Some of these wells, 7, 8, 9,000 foot of water. There's 3,000 to 5,000 barrels of riser volume, right? Can you? The limiting factor right now in some is how fast can you pump, or you could transfer fluid, right? You could design to pump a displacement at 25 barrels a minute, but if you can only bring fluid from a reserve pit up to 10, that's as fast as you'll be able to pump. That's your limiting factor, right? So you have to design to that particular parameter.
Yeah, I mean, you bring up a really good point there in terms of the operational aspects of it and how that may limit the actual operation that you're trying to do. So again, going back to what you were saying earlier in terms of reducing volume, does that help with reducing rig time and therefore costs?
I think so. We can design and build on the rig. So they have the pit space. We have several cases we have to blend the spacers onshore and ship them because the volumes necessary exceed the pit capacity, because you're trying to take every pit that's on the rig to hold completion fluid, right? So those things all come into to factor, and luckily we can minimize the quantity of barrels necessary to spacers to pump due to lower concentrations and contact times.
Yeah, okay, good. So then basically anything to sort of reduce time and cost is going to be a benefit, particularly now in the current environment. Coming back to what you mentioned earlier in terms of the changes after Macondo and the requirements now on fluid density, we have a really good question in from the audience. Azat Gambetov, sorry, Azat, if I mispronounce your name, but a really good question. How do we increase the specific gravity of completion brine from 1.8 to 2.1 as specific gravities there without barite? I mean, that's a great one.
So I got to calculate what that is, because it's been a while since I've been overseas and don't know what that is.
So everybody has to multiply by like 8.6. No, divide by 8. Yeah, multiply by 8.6.
Yeah. So we actually could obtain those with salt. We have some surfactants that'll work with in zinc environment, more of an acidic type environment. We would get up the TADS 1, probably use barite to get up that high, but that's still in the range of brines, but albeit zinc or a more of a CS Neptune system like we have, right?
Yeah, so that's one of your new innovations, right? Is that Neptune fluid? Yeah.
Yeah.
So that's a higher density brine.
Non-zinc, right? Non-zinc, non-formate. But you can do, CS Neptune systems will get you there. Zinc bromide system will get there. Cesium formate will get you there, right?
Yeah. Okay. Yeah. So it's just down to cost and operational limitations, environmental limitations, I guess. Yeah. Again, just quickly going back to, you talked about volumes. I'm just interested in that piece. So again, and maybe a dumb question, why is it so important to try and reduce the volumes that we have? You know, what is it in terms of disposal and fluid management that's
Exactly.
important there?
You know, a lot of the thing, one is pretty much everything you're going to pump is going to go for disposal. So the spacer system itself needs to be smaller, compact. You need to lessen the interface, which usually will go for disposal. We've done a lot of good things in reclamation, but you know, still, you know, it's kind of minimizing waste, minimizing consumption, you know, with the spacer system itself, and then kind of not contaminating the mud itself because it's got value on the front end, right?
Yeah.
But
Yeah, no, absolutely.
there's a lot of cost in waste management.
Yeah, okay, thanks. So we've been talking displacement. So maybe Asher, can you just sort of throw up the photo of what the equipment looks like before a displacement? So there, Joey, talk us through this. What are we seeing here before a displacement?
Unfortunately, that was a way of life for us, you know, prior to our TAD system, right? You know, these are riser brushes and buckets, you know, to catch dirt and all. And you can see clearly there's mud still left on it. You know, this is after our wiper trip. What this means is that we got to pump another space, a secondary cleanup. You know, and you know, I would say it happened more often than not. You know, and after you and I spoke about photos.
Yeah.
I get these photos all the time. The client will deliver them to me quick as can be.
Yeah, I'm sure. Yeah, I mean, they're very concerned about, hey, my wellbore's still dirty. I have to pump another train, and it's like costly rig time. Yeah.
Yeah, and it's usually on my dime, right? So
yeah,
we had to do something different. So we just took a step back, you know, and you know, we got very seasoned hands, you know, in the field, in leadership roles. So it took all of us to sit back and what do we do to fix this, right?
Yeah.
And after we started highlighting these areas where we could work on, you know, we got the smart guys working in our tech center, right?
Yeah.
And I'm very thankful, and we have a good team. Yeah.
Yeah. So Ashley, can you show us the other photograph, what the results look like? So yeah, Joey, tell us what this now is.
So now what you see, you got very clean tools. There's not a hint of mud. You know, you look up on the shoulders on the upsets of the tools. I mean, there is nothing. We didn't drag across anything coming out the hole. It's water wet. The magnet there in the middle is full of little metal particles. The brush, individual bristles on the brush are clean. This is what we see now, right? In fact, I was surprised. I didn't really notice it until I was talking to our director in marketing. I think this is the first set of photos that I received that actually came out of the hole in daylight where you got a good picture. It just seems like you're doing all this work at night all the time, right?
Yeah. Yeah, I mean, they look like new tools, right? I mean, they're that clean. Yeah, that is very impressive. So, I mean, there's going to be a lot of happy operating companies seeing their wellbores being that clean, because obviously that sort of is beneficial to their well operations and production.
So the good thing is that if that's what the tool looks like coming out, you know your wellbores looks like that.
Yeah. No, absolutely. So, obviously, you know, designing the fluid trains is important. Contact time is important. Jim Henrich, just in the chat here, is saying, similar to cementing operations, is 10 minutes contact time enough? So we
design for like 8 to 10 minutes, all kind of stuff. But in truth, when we do our lab testing, it comes off, you know, it cleans up in like 3 minutes, right?
Yeah.
But we try to get 5, 8, 10 minutes, depending on maybe on well design. If it's a straight well bore, I'd be pleased pumping it 5 minutes contact time, right? But you know, you have pipe moving around. It's. I don't think there's a straight well out there.
No, no, not at all. So you hit a really good point there. You mentioned lab testing. So from my days back in oil and gas operations, I remember this being a really thorny question. How can you sort of verbally describe to us what is like a standard lab test to demonstrate that this set of displacement pills will clean the wellbore? Can you just talk us through that?
So first, the standard test doesn't exist. I think we've been working on API subcommittees on what does that test look like. I've had spacer systems tested, client labs, independent labs, and everybody has a different opinion on how to evaluate cleanliness. Give a good example. One evaluation was they were looking how murky the wash pill got, right? So basically how dispersed did the mud get?
Yeah.
And, basically we failed that test because our spacer phase separated and everything was laying on the bottom of the cup. It didn't disperse, so,
Yeah.
but the bob was effectively clean, right? So, now what we do, we have a bob test, which we don't use base oil in front. We just go with the exposure to the TADS 1,
Yeah.
then the exposure to the TADS 2. We don't worry about the viscosify pills behind it, because if anything, they're just going to polymer wet the bob, right? So
Yeah.
what we want to do is the cleanliness and whether it's water wet, right? We've weighed the bob before and after. We target, 99% cleanup, right? And we design to that. Now, the good thing is that we've been able to replicate that in the field, right? Prior with our TDSP spacers, we can design to the same way. We got the same cleanup, but we didn't get those results in the field. I can honestly say today, if I got a good cleanup in the lab, I'll get a good cleanup in the field.
Okay, so the technology in a way is catching up with the lab tests. So it's actually, there's agreement between those. That's okay. That's encouraging because I remember always struggling with the lab tests and trying to demonstrate to customers this is going to be a clean wellbore. Okay, so maybe we can sort of talk a little bit about some examples. I mean, if you could, can you share like a case history with us? What would be a good example?
Yeah, I pulled 3 that I thought they varied, right? And
these are available on the TETRA website, right?
Yes, they are. And so the first one I want to talk, where is it? I want to talk about the solids free one, right? So we're actually able to design a complete spacer train without solids, all brine based additives, and it's here it is. And what we were trying to do is reduce the risk and the cost of the well, to maximize the displacement efficiency and minimize post-displacement fluid cleanup, the amount of time to filter and get ready for the completion phase, right? Yeah. So we designed a TAD solids-free system that would separate the isomer olefin-based fluid. And this is what we also found, that we may need slightly different chemistry to give the most effective cleanup of the different base oils that are being used.
Sure, yeah.
Base oil, right? We cleaned the riser, the service lines. We minimized the mud completion fluid interface and leave the tubulars water wet, right? So we effectively reduced the filtration cycles, had a rapid cleanup time. It was within a circulation and a half of bottoms up, and we minimized the interface, right, on this particular well.
So
it was a 10A calcium chloride system. So it was a relatively light density brine system that we displayed.
So you mentioned that was solids free. So did that? I mean, I imagine that helps with the filtration, right? Because you don't have to worry about barite or other solids.
Yeah, we don't have to worry about some of the wetting agents spending much time with the spacer train that's ahead of it.
Yeah.
So it worked really well. The client was pleased. It was a goal of theirs to, and what they've been doing before, there was a lot of contamination of the polymer, the spacer system just with the pills itself, right?
Yeah.
We actually did a compatibility test, I guess about 4 or 5 weeks ago prior to a displacement, where the client was interested in if I do get oil-based mud into the spacer train, what is going to happen. In the spacer train, each spacer was completely compatible with the oil-based mud. So at 25% contamination of oil mud in the spacer train, it was still effective. And what we were looking for was more of an emulsion or a
Yeah.
conglomeration of fluids, right? 50-50, 75-25, each way they stayed separate, right?
Well, that's quite an achievement, because I mean, you don't want that those two being incompatible and causing you problems, right?
Yeah, if you think about it like this, it's like the internal phase of a synthetic based mud or an oil mud is usually calcium chloride or brine based anyway,
Yeah.
right? And you have the internal phase there. It's just whether that emulsion gets broken. The second one I want to share was on this particular project, we did 5 wells in this project. We did 4 earlier, and then we came back and they had a subsequent well to increase production. This was actually a displacement of our CS Neptune system, right? So we had a 14-4 completion fluid, and we're kicking out the mud directly, right? We had past history with the TAD system. We had up to 15-20% concentration of active ingredient in the spacer system to clean up. This one we had less than 5, right?
Oh wow. Okay. Yeah.
We do not lead with a base oil. The client prefers to have completely balanced spacer train, so there's no differential pressures or anything. We kicked out the fluid. We had within a circulation of bottoms up, circulation of quarter, NTU readings of 20 or less. The contamination interface was less than 350 barrels. Right?
Wow. Yeah. So that's
this
quite
is really this is in 7,200 foot of water, right?
Yeah.
And we reduced the job time by 7 days compared to previous displacements for these projects, right? So we had 4 wells that we did before where we reduced it by 7 days of time, right? We went immediately into the completion phase.
Yeah.
So that was we were pleased. The client was pleased.
Yeah, I mean, that's a really dramatic change in operational practice, that whole time saving there, and just the reduction in volume of chemistry of chemicals and volume of fluids in total, right? Asher, can you just throw up that other cost comparison slide that we had? Joey, is this, I mean, I think this really sort of demonstrates what you're talking about here, right? Can you say a little bit more about this?
Yeah, and so, and the cost savings in here is from the salt necessary to get that fluid back up to density, right? The TDFD system, and this is strictly our system. I'm not talking about anyone else's, right?
Yeah, sure.
But I believe that their problem is the same as mine, right?
Yeah.
This is strictly the cost savings from salts to weight backup, right? So this case 1 is a 10-5 calcium chloride system. TDSP costs were what it is, and it's like 47%, half the cost, right?
Yeah.
You move over to the higher density system where you're having to weight back up with calcium bromide, right? Again, this particular system was zinc free.
Yeah.
And I'm catching it now that it shouldn't have been 14.7. It should have been 14.4. My bad.
Okay.
It's the TDSP system. We were running around, $2,000 a barrel. The TADS one is cut less than half, right?
Okay, so these cost savings here, those were just on the chemistry, on the chemicals?
Just simply the weight material.
Okay, so I mean, in addition to that, so not seen in those cost savings is all the rig time that you'd save, because you're saying that these innovations are faster.
This is just the spacer system. I get evaluated for, despite what I say, I get evaluated on a cost per unit.
Yeah.
So,
Oh, for sure, yeah.
so what I want to show is this is the cost savings in design of the pill, right, to maintain it.
Yeah,
Uh,
okay.
there's rig time. There's volume. Again, if you look on the cost per unit, you're not even considering the lesser volume of this.
Yeah,
And
so these,
when we look at the higher density case, case two, you're going from like 20% volume additive to
yeah.
5%.
Yeah, okay. Yeah, that is a very dramatic change. So also impacts, the sustainability of the operation in terms of environmental impact and stuff. So yeah, all around very positive, very, very positive. So I'm just looking at the questions from the audience. We had another question from Carlos Jonathan Hernandez. And this is a kind of like slightly from left field question, I think. It's sort of, he's asking, what kind of fluid is recommended to demagnetize particles in the well? I mean, is there such a fluid?
To demagnetize,
Yeah, to in the well and avoid trips with magnets. I mean, is that a thing?
uh, not that I know of. I mean, everything's going to have a charge.
Yeah,
You know, uh, I think magnets have proven. I think use of magnets have saved wells, right?
oh yeah.
So I don't know of a way of demagnetizing or knocking the charge out of particles.
Yeah, I don't know many operators that would not want a magnet run in there. They clean up wellbore strings. So, I mean, as you say,
Yeah,
there's a lot of metal sometimes in some of these wells, so you need to get it out.
yeah,
So,
yeah. A magnet in a junk basket will
yeah,
work one.
exactly. So, we've covered the history of displacements and the innovations that you guys have made, and we've seen now just the dramatic cost savings in terms of just the chemicals involved, and there's also additional significant cost savings in terms of rig time and operational time. So, really, sort of wrapping up our discussion now, looking ahead, as the market recovers, what are you excited about in the return of operations, significant operations, Gulf of Mexico? What are the big challenges, do you think?
Big challenges. I think it's we've been fortunate to maintain most of our or many of our offshore workers. Right, we've stayed busy in this downturn. But I think the biggest challenge is trying to get people to come back.
Yeah,
Uh, it's going to be a big challenge. I'm looking forward to. It looks like the clientele itself is changing in the Gulf of Mexico. Which is great. There's new people coming in, and then there's the traditional guys that are out there. The big guys. Uh, so I think it's going to be all working within the infrastructure that's there. There's going to be a few new facilities coming in, but not many.
yeah.
Mostly infield drilling. I think it's going to be much like it is today. I just want the volume of work to.
Of course. I mean, everybody wants the volume of work to pick up. I'm just thinking, on the technology side of things, looking further ahead, we've got the big deep water wells like 20,000 psi type operations. What kind of challenges do they bring in terms of completion operations?
Well, I think it's more in design and engineering. The rig design, even BOP
Yeah,
stacks, the equipment that's going in the hole. Those are things away from what Tetra does. There's a lot of work to be done there, and then it's kind of if you're a service company working within that area of completions, do you spend the money hoping they come, or do you get a sponsor to help you develop this stuff, right?
yeah, for sure. Yeah,
So and with regard to the completion fluid business, it's twofold, right? It's the 20,000 pound 20,000 pound environment or better. Maybe more into the zinc-free systems, or high-pressure systems.
Yeah.
And then on the other side of that, complete opposite, is low-density intervention fluids, right?
Yeah.
Some of these guys are going back into wells that got less than a 7-pound pore pressure now that is bled down. How do you combat that? I think that's focused area for us, as well as the high density fluids.
Oh, okay. No, very interesting challenges ahead then. So yeah, that sounds a positive way of ending things. I just want to pick up one last question from the audience before we close. So Philip Kaufman, he's asking, looking at Tetra's website, one of the components in TADS is a non-toxic biosolvent. What was the initiative behind that?
We just tasked our guys with finding stuff that worked. Personally, I never asked what they're doing. It's on a need-to-know basis here. I just wanted a low concentration additive that was very effective, right? But it's I can't tell you what the biosolvent is.
Okay.
I don't know. I can tell you what was in in some of the other stuff because I helped purchase it, sell it, develop it. Right. This is completely. Here's the task at hand. You guys get it done. Right.
Yeah. Again, I got to take one more question from the audience because these guys keep bringing them in now. They're starting to get interesting as well. So, John Etim, he's asking, has your technology been applied to an extended reach well? If it has, how efficient was this?
I can't say that. It's deeper wells. The Gulf of Mexico, we really don't have that many extended reach wells, if you will, right? And you're talking about long reach type stuff.
Yeah.
Most of what we're fooling with is subsea trees. We got a few TLPs that we're working from. They're angled, but they're not extended reach well. So I'm going to say not, but I would say we know how to do them, right?
Yeah.
Then it comes back again into design and modeling, which we didn't talk much about today, but I mean, software is a big part of what we do, right?
Yeah,
designing,
of course.
modeling, see what it looks like. Goes back to working on that TDS, the TADS 1 spacer, and the rheology on it. We don't want it to channel.
Yeah, absolutely. Yeah, I mean, as you say, it's all about that operational sort of the operational parameters. I was going to say the pump speeds and the spacer size and stuff like that. Yeah. So Joey, as we wrap up here, any final thoughts, comments that you want to leave the audience with?
I'm just pleased to have made a career in this industry. I think been quite fortunate with my travels and the positions that I held, the folks that I meet. And Niels, you've been here a while. It's a small world. You keep recycling people. You keep running across them, right? But I think Tetra is a very small niche company or completion fluids company. We think of ourselves as problem solvers. If there's something that you need to work on and that's been troubling you, just give us a shot. I think that we can help you. We find solutions for clients that we can't really work for because of the location, maybe, right?
Yeah.
But we help them do things better, and so we're here to serve, right?
Oh, no, great message. Thank you very much. Yeah, we're here to serve, and we're engineers, and we like to solve problems. Yes, absolutely. I think that's us as an industry in a nutshell there. So, Joey,
I just want to say this real quickly, right? Because it's not
sure, please.
I have guys that really are good at what they do, and then they try to think. And a lot of times, and it may be a recommendation of change, and people don't like change, right? So it was the hardest time to get some of these guys to, hey, look. You see a train wreck coming and you're given a recommendation, but if at some point you got to design to repair the train wreck, right?
Yeah.
So, we're again, it's if you can't fix it, then you got to prepare to fix it, right?
Absolutely. Yeah. You always got to have a contingency. Yeah. But I think engineers are good at that also.
Yeah.
Joey, it's been a real pleasure talking with you today. Thank you very much for bringing to us completion fluids technology and displacement. It's been really, really good. Thank you.
I appreciate the opportunity. Thank you, Niels.
All right,
Thank
thank
you,
you. And
SPE.
thank you, audience. You've been great, audience, so thank you. Please join us later in the week. We're talking Latin America outlook and oil and gas in Latin America. So thank you very much. Thank you, Joey, again. Thank you. Have a great day.
Ciao.
Ciao. Bye.